And the day is finally here where we get to talk about materials and specifically mechanical properties of materials. And it's kind of the section hopefully a lot of people have been waiting for. So eventually we'll sort of break things and fracture. Actually, we won't get into that too much in this course, but anyways, the key idea here for when we're looking at stress strain of materials, the way that you want to be careful of a couple of things. One is sign notation, and then the other is units. So be very, very careful, cautious. We'll get into all this in a second, but this might be a little bit different from if you've taken a material course before, if you haven't seen stress and strain in kind of this tensor notation format, but we'll get into that in just a second. So when we're dealing with basically mechanical materials, and in this lecture is the essential here is we're building the framework for how we treat stress and strain. And in this class, in lecture 9, we are going to get into, okay, given these linear elastic equations where we could actually apply these fundamental equations, how can we now build instrumentation in order to kind of validate and experimentally measure stress, strain, and all these other kind of properties that we're going to talk about today. So that's going to involve circuits, but this lecture is really, really critically important in order to kind of get this fundamental and sound foundation. So let's talk about sign conditions to begin with. So if I have a material and I am extending it, I'm pulling it, uniaxial tension test, that material is going to change their dimensions. It's going to increase the dimensions. So when we're in tension, we are going to say that this strain is positive and then that stress is positive as well. We'll get into stress and strain. Hopefully people know stress, force per unit area. What are those units? Newton per meter squared. We could also call that a Pascal. We know that strain, we're going to see this in a second, change in length over initial length, engineering strain, engineering stress, those in a second. So meter over meter equals unit less, or sometimes it could be expressed in percent. Be careful on which notation you kind of see. But anyways, when we're in tension, this is going to be positive. If we have a material like this and I am pushing it like this, it is going to be in, at least we want to always draw out our coordinate system. So we'll see that the stress in the 1-1 direction is going to be negative, and the strain in the 1-1 direction is going to also be negative. So tension, positive, compression, negative. Also, if we are counterclockwise this way, this is going to be positive. If we are clockwise, that is going to be negative. So this won't matter too much, and we're not going to do a lot of kind of rotational or torsional kind of components from stress and strain, but this will make a big difference when we're talking and rotating our coordinate systems. So a little bit more on that a little bit later on. So stress strain curves. So hopefully people remember this from material science. So let's look at it here, one right here, right here. So let's identify some key regions. So here and right here. So this first region is our elastic region. This is second region is our plastic region, and our third region is our fracture region right here. So what's happening, we want to look at, again, what's happening atomistically and what's happening macroscopically in each of these regimes. So in our elastic regime, what are we looking at atomistically? Well, atomistically, you see, or actually, let's look at this kind of curve here. So remember, these are in typically in units of pascals. We're going to leave these unit less, not in percent. So this is one kind of dangerous expression. In this elastic regime here, you can describe the relationship between stress and strain using Hooke's law. And the slope here is going to be our, the slope here will be our Young's modulus. So our Young's modulus is, when we think about material properties in terms, this is going to be stiffness. So the stiffness of my material, or stiffness. I misspelled that. Anyways, typically, if we're dealing with metals, they'll be on the order of hundreds of gigapascals. Steel can be 200. So steel, 200. Al 61 is 69 gigapascals. So metals. Ceramics, you could be on the order of 200 to 300. Again, these are general rules. Obviously, there's materials that vary. There's always exceptions to material rules, but tungsten is our stiffest material. So that is why you get in an SEM, they're tungsten filaments because it has the highest melting temperature of all materials. And then finally, for polymers, These can vary. Again, most difficult material to kind of study. These can be on the, usually you could approximate it as 1 GPa, but they can be from like 10 kPa to 1 GPa. So large differences there, but in this class, you can kind of always use this approximation. So in some problems, you will not be given a Young's modulus, so you can kind of assume it. Now, this is a dangerous expression. People think that this is the beginning and the end of mechanics of materials. This is not at all. This expression only holds for this very specific loading state, uniaxial tension. That's it. This is the only time when this expression can be utilized. And really, the expression should be written, as we're going to see here, like this. But we'll get into that in just a second in terms of our mechanical properties. So what is happening in my elastic region on the atomistic length scale? Well, atomistically, I'm pulling on bonds, but I'm not breaking any bonds. So I'm just stretching. So I have all my atoms right next to each other. When I pull, I'm stretching those bonds, but I'm not breaking them, and I'm not moving. There's basically no dislocation motion. So dislocations, hopefully you know from material science, edge dislocations, like here. The dislocations are present in this elastic regime, but they are not moving. When I'm pulling in the elastic regime, I'm still just stretching. So nothing's happening there. I'm not breaking bonds. I'm not moving any dislocation motions, even though dislocations are there. And macroscopically, when I pull on this material in the elastic regime or in the elastic stresses, I'll pull on it and it'll stretch. But then when I remove the load, it will recover the exact same dimensions. So there is no permanent or plastic deformation. It just basically pops back into place. So in this regime, the elastic regime, I have equations, and we're going to develop a set of equations where we can know and relate the stress to the strain in that material, and vice versa. So there are basically equations and a framework that we're going to, basically it's linear isotropic elasticity equations that we're going to be able to kind of relate. In the second regime here, in the plastic regime, what's happening macroscopically? Well, macroscopically, now when I'm in the plastic regime, when I pull on this material and I unload it, the materials change dimensions. There's permanent or plastic non-reversible deformation. And atomistically, we are not breaking bonds yet, but we are starting to, well, kind of breaking bonds, but we are basically starting to move dislocations. So dislocation is, bonds are starting to be broken or moved around, but we're not creating like huge voids yet. But bonds are being broken, and then dislocations are starting to kind of move. We're initiating dislocation motion here. So that's the key aspect here. And in the second regime, we do not have any, these are all empirical theories. So we do not have any kind of framework or kind of first principle equations that can relate stress and strain here. So, and additionally, these are some, we'll talk about strain hardening in a second. But I forgot to mention the first regime. So we could identify the stiffness here. So Young's modulus, we'll talk about language in just a bit. Young's modulus is a measure of stiffness. But we could also here measure, this is our yield strength. This is our yield strain. Here, we could identify the ultimate tensile strength, UTS. So UTS is just the highest stress in your material. So this was supposed to be a little bit higher, and then it goes down a little bit. So the sigma UTS is your ultimate tensile strength. It's the measure of how essentially strong the material is. It's maximum stress that's exhibited in your stress strain curve. So it doesn't have to necessarily appear here, but it's just the maximum stress. At that maximum stress where you see kind of this increase in stress and then a drop off, this is also, when you see that kind of that dip, that is where necking occurs. So when the material starts to really thin out at the center. And again, unfortunately, you can't see that in our kind of lab component, but hopefully there's going to be a video soon that will kind of show you that necking phenomenon. So it's where you're at the, you typically have a sample that's a dog bone shape, like a dog bone. It's a poor dog bone. But when you pull, you eventually reach a point in that plastic regime where the neck starts to thin out. So it starts to really narrow here and elongate. So this, where you kind of hit that peak and then start to drop off, before that drop off, that's where necking is initiated. So it's really, really cool when you see it in person. And finally, again, you can kind of see sigma UTS, yield stress, yield strain. Again, this is also a measure of kind of, toughness or strength of a material. And then finally, we hit our third regime, which is fracture. So now we are not only breaking bonds, we are, again, here you go, you can see yield stress, yield strain, ultimate tensile strength, onset of necking. And here, again, now you can see the fracture strength, fracture strain. This is also a measure of ductility or brittleness, depending on how large that value is. So again, fracture stress, fracture strain. This is where material catastrophically fractures. So we're breaking bonds. We're creating huge, basically your material, I pull and I create two different surfaces. And if you're in my polymer class, you know that creating surfaces is always bad energetically. So this is very, very unfavorable to create two surfaces. But again, the strain energy is so much that the bonds are being pulled that this is a much more preferred energetic state than to kind of that elastic strain energy that's kind of built up in the material. Yeah, so we can now, there's a couple other properties that we can kind of look at in the stress strain curve as well. So one is this elastic strain energy. So elastic strain energy, and that is just the volume of your material times the integral from 0 to EY times sigma dE, sigma EdE. So it's just essentially this integral under this curve right here, skipping around a little bit. So elastic strain energy. So we call this an energy. Energy, usually we are talking about units in joules. So why is this in units of joules? Well, let's look at it. So stress is in units of what? Pascal, so Newton per meter squared. If I look at the area under that curve, so it's unitless. So if I integrate, the area is just Newton meter squared. Now if I multiply by volume, meter cubed, this gives me joules, which is energy. So that's kind of why, again, elastic strain energy. So this is essentially the energy that's stored in the bonds that you're stretching right before you start to, again, break bonds and or start to move dislocations. So this is the elastic energy stored in your material. You could also look at toughness, and that's going to be volume times 0 epsilon F sigma strain D. So this is the total area under the curve. So this is the energy required the total energy required to fracture and break a material. So it's all the energy stored in your material up to the point of fracture. So again, these are the the units, or not the units here, but the basically you could calculate toughness or elastic strain energy here. All right, now let's talk about language. Language is very, very precise in material. So when we talk about stiffness, we are talking about the Young's modulus of our material. So higher the Young's modulus, the more stiffer the material is. If the Young's modulus is low, we call it compliant. When we talk about strength, we could either be talking about yield strength or ultimate tensile strength, or the fracture stress, or you could even be talking about sigma F. So this is a very dangerous kind of when we talk about strength. So you want to be specific. So you don't want to say strength or how strong material is. You want to specify, are you talking about yield strength, ultimate tensile strength, or fracture strength? So that's very, very important. Also, we'll talk about a ductility of a material. So if a material is ductile, it's able to kind of stretch. Hopefully you've kind of heard that term before. But when we talk about ductility, we are talking about this epsilon sub F. So how ductile it is. If our sigma sub F is very, very, very low, it is like for ceramics, it could be like 0.1 or less. So if it's very, very low, we call that material brittle. If you have polymers, where epsilon sub F is around, could be 10, that is very, 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 very ductile. Nice. So not stiff, compliant, not strong, it's weak. Material is not tough. It could be brittle. Again, toughness and brittleness, we'll talk about that a little bit later on. Hopefully this is some nice review on basically stress strain curves, and hopefully it gets you back into the materials mode. So we're going to be getting a lot deeper into this in future lectures, so make sure that you're familiar with stress strain curves. If you leave nothing else from this course, I want you to be able to kind of ace a stress strain curve question on an interview. So hopefully this helps. And if you have any questions, please let me know, and I'll see you in the next video. Thanks. Bye.